So let's use this electro-harmonics pedal as a reference for the passive octave circuit that we're going to make today. There's three controls. There is volume, there is boost, and there is octave. There's a switch here that allows you to select between 9 and 24 volts. I've got it on the 24 volt switch right now, so the green signal is much larger. Let's just switch it here, and you can see the signal goes down a bit, and then I put it over here and it goes up again. I've got the boost turned down, and so you can see there's a slope, so the clipping is not as harsh as it could be. So if I turn the boost up, this turns into a square wave, generating lots of harmonics to create that gorgeous fuzz sound. So now let's blend in some octave, and so I just turn this up, and you can see now the signal is doubled. So we have two tones essentially. If we looked at it on a spectrum analyzer, you'd see the fundamental, and we're generating a 1 kilohertz sine wave from the signal generator. We'll turn it down. So this frequency is 1 kilohertz, and we'll turn it up. And now we're essentially doubling the frequency. So you can see there's two frequencies there. And so that essentially is a 2 kilohertz signal superimposed on a 1 kilohertz signal, and that is essentially the sound of the octave. That's what we're going to try and emulate today with a few passive components. I found this schematic on Fuzz Central. Given the name of the website, I'm guessing it is a fuzz, but even just by inspecting the schematic, it definitely looks like there's a lot of good gain here. They will be turning a sine wave that goes into the input into a square wave that's lush with lots of harmonics, giving us the wonderful fuzz sound that we all love. It looks like there's two gain stages here. This looks like a buffer. The business end of this circuit for octave is this part here. So it's 3 or 4 components essentially. So we have a 33 microfarad capacitor. This is going to AC couple the circuit to the transformers, only letting through AC. Transformers love AC because that's how they work. And then it's also going to be quite bassy. The low frequency response of this is pretty good because it's a very large capacitor. On the output of the transformer, we have the center tap to ground, and then the two other taps go through a 1N34A diodes, each one on each tap. Then they mix together, or they're joined together, and go out the volume. So what this does, if we put a sine wave in here, what it would do, it would what you call partly rectify the circuit. So if you imagine a sine wave like this, what happens here with this circuit is that the bottom of the sine wave will be flipped to the top, and we'd end up with a bunch of humps. And those humps essentially are the doubling of the frequency, hence giving us our first octave signal, which is what this is designed to do. So let's get this wired up, pump a sine wave in, and let's see what the output looks like. So I've assembled the circuit on my prototyping system. Right now, I'm bypassing the circuit, and you can see the pure sine wave, the 1 kilohertz tone, going into the oscilloscope. I've got the coupling capacitor here. This is a 10 microfarad as opposed to a 30 microfarad. Don't think it's going to make much difference. I've got the primary end of the transformer on the output. I'll swap it around and see what happens later. And then here are the two diodes that are making the frequency doubling process happen. So the 1N34As. These are classic germanium diodes, by the way, used in circuits such as a clon, and we'll measure the performance of those later as well. So let's engage the circuit, press the foot switch, and there you go. Now we have moved from a sine wave like this to humps at double the frequency. So we have created a frequency doubling circuit, or an octave circuit, so that would represent the sound of the first octave superimposed on the original tone, which is 1 kilohertz. So it's 1 kilohertz and 2 kilohertz now. And if we had a spectrum analyzer, we could see those two tones, probably more tones, because we're adding distortion. I've taken the 1N34A now and put it on my component tester. We'll do a more comprehensive video on using a curve tracer for understanding how germanium components perform, not only diodes, but more importantly, transistors. Because if you're going to construct fuzz with germanium, you really have to understand the performance of each transistor as they do vary. So let's hit this test button and let it make a measurement. And here's the measurement. So 365 millivolts is the voltage drop. So that's in line with the typical spec for germanium diode or a germanium junction has about a 0.3 volts as opposed to 0.7 volt voltage drop for a silicon. I've added the Konkordsky fuzz now, and so let's put the fuzz on. And you can see there we've got some symmetrical clipping with this setting. We can move it there to asymmetrical. Symmetrical. This is I did a previous video about changing the input impedance and getting different types of distortion characteristic. So that's the full fuzz there. Now let's engage this. That's interesting. You can see some extra frequency components here. A little lower in frequency, it looks like, but the main component, eyeballing in the time domain, looks about the same if I adjust the fuzz to symmetrical. So we get some nice frequency doubling there as we move to asymmetrical, which kind of tells me that this circuit prefers to be prefers a symmetrical signal as opposed to an asymmetrical signal that a typical fuzz face produces. So let's drill down on that a bit more and see how we can modify the circuit to get a good fuzz face distortion. Just for fun, we swapped the transformer around, so the primary is now facing the fuzz, and you can see if I press the button, there's no difference. And that's because this has a 1-to-1 windings ratio, and it's 10k on the input and 10k on the output. So it really doesn't matter which way you have the transformer facing. Let's play with it. So now I've mounted those components in a box, all hand wired by me. And let's try it. So without the Octave engaged.